Suppose a fly was living in R3 and it was sitting at the origin, the point 0, 0, 0, and it wanted to get to a light bulb that it saw, which was sitting at the point 2, -1, 1. And so the question is, can this fly get to that light bulb? Now, this fly is only able to move in the direction of certain vectors. So it can move in the direction of the vector 1, 0, 0. It can move in the direction of the vector 0, 1, 0, and it can move in the direction of the vector 0, 0, 1. And finally, it can move in the direction of the vector 1, 1, 1. So can it get to that light bulb only being able to move in the direction of these vectors? And I should add that being able to move in the direction of these vectors means that it can move either sort of, in the exact direction of these, but, scaling upward, or in the exact opposite direction, namely by scaling them by some negative value. And so you might pretty quickly figure out that, sure, this fly can get to the point 2, -1, 1. It could first, for example, move, by a scale of 2 of the vector 1, 0, 0, which would put it at this point here, 2, 0, 0. And then it could move sort of in the -1 direction of that vector 0, 1, 0, which would put it kind of directly below the light bulb. And then finally, it could fly up by the vector, in the direction of the vector 0, 0, 1, and it would get to its light bulb. And so you can see, kind of maybe showing you a few angles here, you could see that our fly can get up to that light bulb by just moving by those vectors. One thing to point out here is that we never used the vector 1, 1, 1. So we only needed those first three vectors in order to accomplish this goal. And we could actually, no matter where that light bulb is, we could accomplish this just by using those three vectors. So this fly could just sort of move in the direction or exact opposite direction of each of these three vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1, and get to any point in the space R3. In terms of linear algebra terminology, we would say that that R3 is the span of these three vectors. It's also the span of the four vectors if we add in 1, 1, 1, but that vector was somewhat extraneous. We didn't need it to get to every point in R3. What if instead of being able to move in those four vector directions, we actually eliminate two of them? Okay, and so now we've got just the vectors 1, 0, 0 and the vector 0, 1, 0. Our fly could get sort of directly below that light bulb by moving 2 in the direction of 1, 0, 0 and -1 in the direction of 0, 1, 0, but it couldn't fly up to that light bulb. We sort of need that third vector in order to get to that, sort of additional height there and fly up to it. So what we've seen kind of is, we can get to every point with these three vectors. If we added a fourth vector, we can still get to every point, but we don't really need it. If we removed two of these vectors, we can no longer get to every point. So it sort of seems like those three vectors, and it doesn't have to be those three necessarily, but kind of that number 3 is important here, are what allow us to get to every point in R3. And so what we are kind of starting to allude to here is the concept of a basis, namely a basis for R3 here could consist of these three vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1, because those three vectors are sort of enough vectors to get us everywhere in R3, and not too many vectors that we could eliminate one and still get everywhere. So being enough vectors is kind of a concept of being able to span all of R3, and not being too many is getting at the idea that this set of vectors is linearly independent. So we're going to define more formally this concept of a basis in a future video. But for now, you can hopefully see with this example that our goal is for our fly friend here to be able to get to that light bulb, no matter where it is, and sort of have so be able to span all of our three, have enough vectors to span all of our three, but not have um, not have too many vectors where we sort of have extraneous directions that our fly could move in. So we want those vectors to be linearly independent, and the magic number for R3 is 3 vectors. We're going to explore this concept of a basis and that magic number for other for other spaces, so maybe R2 or R4, and potentially what are known as subspaces of these different Rn spaces as well. So this is just kind of an introduction to that concept of a basis, a set of vectors that is both linearly independent as well as span. So enough vectors to span whatever space we're interested in, and not too many vectors where they're still linearly independent. So kind of getting at that perfect right number, and we'll more formally define this concept in a future video.